Section 15.7, Part 2 in Thomas's textbook, and it's part of 15.7 and 15.8, but Part 2 in Stewart's textbook. Now that we know a little bit about spherical and cylindrical and Cartesian coordinates, we would like to see how triple integrals in cylindrical and spherical coordinates look like, given that we have seen what the triple integral in Cartesian system or rectangular system. Notice the integrand is a function of x and y and z, but the volume element is dz, dy, dx, and 5 other permutation of this 3 factors. Remember, there are 3 factorial ways of permuting what? The order of this integral, depending on which view, from which perspective you're looking at the solid. Turns out in cylindrical coordinates, the function of x, y, z becomes function of r theta z, and the volume element becomes r dz, dr, d theta. However, z goes from surface to surface, r goes from curve to curve, and theta is constant. But the surface has to be expressed in terms of functions of r and theta, whereas the curve has to be expressed in terms of what? Let's say just theta, correct? So this would be some function of theta, and this would be some other function of theta. And theta goes from what? Theta 0 to theta 1. In a spherical, the integrand is a function of what? Rho and phi and theta. But the volume element is rho squared sine phi d rho d phi d theta. So that's the volume element. Rho goes from surface to surface, which has to be function of theta and rho, phi. And phi goes from what? Phi 0 to phi 1. And theta goes from theta 0 to theta 1. So notice the last 2 integrals, they have constant limits. Unless you have a translation, then phi will change, but that's a different story. So the question is, where exactly these volume elements for cylindrical and spherical coordinates come from? Well, if you take a piece of a cylinder and cut it out, and take that piece and zoom in to it, you will see this piece. Notice you have the width of it. So it would be like, if you would like, open it and roll it out, you will see a rectangle with a thickness. The width is d delta r, but the length is arc length here. Remember, arc length of a circle was what? R times theta. That means radius times what? The central angle. In this case, the central angle is delta theta. Radius is r. So this arc length is what? R delta theta. The thickness is delta z. So to find the volume, you have to multiply length by width by height. And when you do this, you get this expression. But if delta z and delta r and delta theta are small enough, then delta z becomes dz, delta r becomes dr, delta theta becomes d theta. And lo and behold, you get what? Volume element as r, dz, dr, d theta. So that's geometrically where it comes from. Of course, there's a theoretical reason for it. It's called Jacobian of transformation. So this R is called Jacobian of transformation, and that would be discussed in different video. For spherical, okay, to take a piece of a sphere, like a basketball, you need to make 2 cuts. One from what? In the direction of North Pole to South Pole. And the other one is like, going around the basketball, like let's say from west to east, let's say. So therefore you need 2 cuts, one from top, one from the side. Then again, you're dealing with two arc lengths. So one of the arc length is what? R delta theta, but R in the spherical coordinates is rho sine phi delta theta. The other one is rho delta phi. So these are arc length. And the length of this what? Piece of sphere, volume element, is delta rho. Once again, if you kind of cut this and roll it out, you'll see a rectangle with a thickness. So the length is rho sine phi delta theta. The width is rho delta phi, and the thickness is delta rho. So if you multiply length by width by height, you get this. And lo and behold, that would give you rho square sine phi delta rho delta phi delta theta. If these three factors are small enough, then you can what? Then you can conclude that the volume element is what? Rho square sine phi d rho d phi d theta. So let's see an example quickly and see how these triple integrals apply to specifically a volume problem. Suppose you like to find the volume of a solid which is bounded by cylinder and this circular paraboloid which opens upside down, and the plane z is equal to 0, x is 0, y is 0. So in other words, you are in the first octant only, and they want you to find the volume in the first octant. And they want you to use cylindrical coordinates. So what you do, you draw the cylinder, and here's your upside down elliptic paraboloid, or circular paraboloid in this case. So you need what? The volume of this solid, which is within both of these surfaces. So remember, volume is what? Is triple integral, and the limits will be over a solid, and the integrand will be 1 dv. But remember, dv in cylindrical coordinates is r dz dr d theta. So it looks to me z goes from what? Floor to the circular paraboloid, which is 9 minus x squared minus y squared. But if you factor out the minus, you get x squared plus y squared. But x squared plus y squared is r squared. And as far as the limits for what? R and theta, as you can tell, you get a quarter of a circle on the floor. So r goes from 0 to 2. That's the radius of the circle on the floor. And theta goes from what? 0 to pi over 2, because you're dealing with quarter of a circle. Remember, you're in the first octant only. Everything is positive, correct? First octant in space, that's kind of analogous to what? First quadrant on the floor. Then you evaluate this, then you get 7 pi cubic units. So therefore, the volume of this so-called solid bounded by these surfaces in first octant comes up to 7 pi cubic units. So depending on how you measure these factors, or the length, height, and the width, then you would have cubic units like cubic feet, cubic inches, and so on and so forth. All right. Question arises, when do I know to use cylindrical coordinates? Cylindrical coordinates are useful in rotational symmetry type of problems. Example 1 would be water flow in a round section of a pipe. Heat distribution in a cylindrical metal. Electric magnetic field produced by electric current in a long cylindrical wire. So these are the kind of applications where it would be nice to use cylindrical coordinates. So notice all of them has some sort of cylinder involved in it. As far as the spherical coordinates, let's see how would you find the volume of a sphere, which is what? Which is center at 0, 0, 0, and the radius is a. So therefore, the equation of the sphere is x squared plus y squared plus z squared is equal to a squared, and a is positive. Once again, in general case, volume is what? Triple integral 1 dv, but the volume element in the spherical coordinates is rho squared sine phi d rho d phi d theta. Keep in mind, rho goes from what? 0 to the sphere, which is a. Keep in mind that x squared plus y squared plus z squared is exactly the same as what? Rho squared, and that's equal to a squared. So that implies rho is equal to a. In other words, this is the equation of the same sphere in the spherical coordinates. So therefore, you're going from the origin to the sphere whose radius is a. Keep in mind, phi can only go from North Pole to South Pole, and phi here in the North Pole is 0. On the floor is pi over 2. And in the South Pole, right here, is pi. It cannot exceed pi. So you go from 0 to pi. Theta can go all the way around, so 0 to 2 pi. Now you would evaluate this with respect to rho first. So you get rho cube over 3, but rho goes from 0 to a. Then you evaluate the second integral as you go from right to left. With respect to phi, don't forget you have a sine phi. Antiderivative of sine phi is negative cosine phi. Evaluate that between 0 and pi. Lo and behold, you get this. Evaluate antiderivative of d theta, which is theta. But theta goes from 0 to 2 pi. So the final answer is 4 pi over 3a cubed. And that's kind of confirms the formula for what? For sphere, which is 4/3 pi r cubed. In our case, r was a, so therefore we have a confirmation of what? The answer. Applications, the system of latitude and longitude that divides the Earth's surface into a grid for navigational purposes is the places we use spherical coordinates. In other words, spherical coordinates is the what? Idea behind the GPS, and that's how you find a specific address on GPS. Very good. So let's do one more problem, a couple of more problems, and we should be A-okay for this section. The question is evaluate this triple integral. Notice it's not a volume problem. As if it was a volume problem, the integrand had to be equal to 1, not x, y, z. So at this point, we don't know what is it that we're evaluating. They just told us evaluate. Evaluate means find the value of this integral with this integrand. They want you to use spherical coordinates. However, the solid is bounded between two spheres. Remember these, when rho is constant, those are the equations of the spheres in what? In Cartesian coordinates. It is x squared plus y squared plus z squared equals 2 squared, which is 4. And x squared plus y squared plus z squared, 4 squared, which is 16. So these guys are spherical equations equivalent to what? Cartesian equations in terms of x and y and z. So the solid is bounded between these two spheres, but below what? The cone. Is that right? So, okay. So I made a little correction here. So it should read the solid is bounded between the spheres and the cone, which the equation of the cone is pi over 3. And phi is equal to pi over 3 in spherical coordinates. In other words, we like to find this volume here, which is trapped between two spheres and the cone. Okay, so remember the way I know this is the upper half of a cone. Remember when phi goes from 0 to pi over 2, but less than pi over 2, you get the upper half of a cone. At pi over 2, you are on the floor. Between pi over 2 and pi, you get the lower half of the cone here, so you get the upper half. So we are trapped between the what? Cone and two spheres, correct? So what you do is, by the way, to see why this is a cone, remember tan of phi is equal to r divided by what? Z. But tangent of 60 degrees is square root of 3. So if you manipulate this, you get z is equal to 1 over square root of 3 times square root of x squared plus y squared, which is the equation of the upper half of a cone, because you only get positive square root of x squared plus y squared. So this is not a volume problem because the integrand is not 1. So what you do, you replace the x with its equivalent spherical coordinate expression, rho sine phi cosine theta, y with rho sine phi sine theta, z with rho cosine phi, and the volume element is rho square sine phi d rho d phi d theta. However, you are trapped between two spheres, so rho goes between 2 and 4. Remember, these are the radii of the sphere. Okay, 2 and 4, those are the radii. Phi goes from 0 to what? To pi over 3. Why is it pi over 3? Well, remember, we were told so, because remember, you always go from North Pole all the way till you hit the cone. And we were told that this guy stops at pi over 3. So therefore, you go from 0 to pi over 3. Theta goes all the way around, so that's 0 to 2 pi. Now you have to what? Kind of multiply these guys out, get a nice expression. First thing I do is what? Multiply the rows. So I get rho what? To the fifth. But when you take the antiderivative with respect to rho, you get rho to the 6 over 6. Evaluate this between 2 and 4. You get what? Some constant times what? Sine cubed, because remember you have 3 sines times cosine of phi, cosine of theta, sine theta, d phi, d theta. The next item is what? Evaluate the what? Integral with respect to phi. So forget about cosine theta and sine theta. If this is u, the u is sitting right next to it, so that's sine to the 4 phi over 4. Evaluate between 0 and pi over 3, so you get other constants. And finally, if you let u be sine, du is sitting right next to it, so this guy is sine square theta over 2. If you evaluate the last integral with respect to theta and go from 0 to 2 pi. However, if you evaluate sine squared theta over 2 between 0 and 2 pi, you get 0. So the entire answer comes up to 0. And don't panic, we weren't supposed to come up with a positive answer because this is not a volume problem. Who knows what this is? So it all depends what this integrand is. So in this particular case, I came up with 0 for an answer. So it's okay, because you must have had some sort of symmetry, things got canceled out, and you got 0. The last problem is find the volume of what? Solid bounded by sphere and the cylinder. In other words, you have inscribed a cylinder into a sphere. Think of it as you have inserted a PVC pipe into a basketball. So we like to know what's the volume of this PVC, which is bounded by the basketball on top and bottom. Remember, if you solve the equation of a sphere for z, you get z is equal to plus or minus square root of 4 minus x squared minus y squared. The positive is the upper half of the sphere. The bottom is the what? Negative square root of 4 minus x squared minus y squared is the lower half of the sphere. Okay, so because this is a volume problem, the integrand has to be 1. In this case, they want you to use cylindrical coordinates. Okay, then you would go, okay, so we're going from what? Negative square root of 4 minus x squared minus y squared, which is the bottom of the what? This, looks like a pill, which is like a medicine. The bottom is the sphere, so is the top. So you're going from negative square root of 4 minus x squared minus y squared to positive square root of 4 minus x squared minus y squared. However, if you intersect these two surfaces, you remember x squared y squared was equal to 1, so replace this guy with 1. So that means z squared is 3. Go back to this equation, replace the z squared with 3, and lo and behold, you get x squared plus y squared equals 1. So in other words, the region is what? The intersection of two surfaces is a circle whose center is at 0, 0, and the radius is what? 1. So r goes from 0 to 1, and theta goes from 0 to 2 pi. Evaluate this, and you get this kind of answer. Please remember, do not change these guys to decimal form because that would be the approximation. We need the exact answer for, specifically volume problems. Incidentally, I could have gone from what? Do the upper half of the volume due to the symmetry multiply by 2. In other words, instead of going from negative square root of 4 minus y squared, I could have gone from 0 to square root of 4 minus y squared. This would what? Evaluate the volume of the upper half, but then due to the symmetry, you multiply by 2. On the other hand, if you go quarter of a circle, like 0 to pi over 2, so this is like what? 1/8 of the volume of this solid. You're trying to find the volume. Multiply the answer by 8. Believe it or not, these three answers should be identical, which is 4/3 of pi times 8 minus 3 square root of 3. Once again, that's called exact form, so please do not change this to decimal because that would convert your answer to approximation, and we need exact answer. Thank you.